Hello, my name is Thorsten from Nokia in Germany. Today I want to talk about the topic of sensing the world for digital twins in 6G. Digital twins are emerging from the vision of the interconnection of the physical and the digital world. These create a lot of possibilities to augment human capabilities. Sensing is an enabler for it, so it provides the context information for those digital twins. So detecting options, objects, humans, object properties, and then also supporting the creation of interactive real-time maps of the environment. Here in this context, we see sensing as a solution to be embedded into cellular communication systems for an integrated communication and sensing system. So the sensing here in this work would be based on the RF signals, which are also there in the bands for communication systems, but of course can be enriched also by sensor data fusion from other modalities.
Let's recap Nokia 6G vision. The vision is that three different worlds become connected. The digital world is our world reflected in software. The physical world is consisting of hardware, of robots. The human world is the wetware, is the biological world. And by connecting these worlds, we can leverage a lot of advantages to have a digital twin representation of the real world for more intelligence, better control, and new experience. And now the communication component of a joint communication and sensing system would be that we have the connectivity to connect those worlds in real time with extreme requirements, so high reliability and extreme high data rates. And the sensing part of it would be that we are able to sense the world, to provide the context information, to create a digital map of our environment, which is a prerequisite of creating the digital twin. Now let's have a look what we already can do with 5G based on Nokia Bell Labs technology. Here you see a picture of the test factory Arena 2036 in Stuttgart, Germany. On the top left side, you see a robot driving around in this test factory with 5G modems. We have installed 5G in this factory and multiple 5G access points which use time difference of arrival methods and angle of arrival methods in order to determine the position of this robot just based on the signals, on the cellular communication signals. And while we are localizing the user, we are also communicating over 5G. So the video is also uploaded at the same time in 5G. On the right side, you see the green dots, which represent the location, so the estimated location of the robot. And they are in more than 95% of the cases more accurate than 50 centimeters. And this localization will help us to offer new service capabilities which are attractive to vertical industry players inside factories. But we will not stop with the capability of localizing. The next thing we want to do for 6G systems is the possibility to not only localize objects which are part of the network, but the vision for 6G is to be able to sense objects which are not even connected to the network, or any type of object. So let me explain you the example principle of how the network can act as a sensor. On the left side, you see a set of base stations. They are sending out signals for communication purposes in order to transport data to users. But at the same time, any object within the communication also causes reflections. So these base stations can pick up the reflections and process them in a way which is similar to existing radar technology. And then we can not only use conventional radar processing, but also any kind of AI/ML processing in order to classify objects, detect objects, localize objects, estimate their properties, etc. In order to make this happen, we want really to integrate the entire sensing functionality in existing communication systems. Communication systems are using slots for structuring the resources in time. And we can either reuse all the existing data communication, or we can also, in new standards in the future, insert new sensing bursts, so new predefined symbols, which then can be used in order to scan the environment, in order to and the scanning helps then to pick up the necessary reflections. These bursts should be very short in time because we want to have a minimum communication service interruption, so we want to still optimize the latency of the communication system. And at the same time, they should be wide in bandwidth, because the wider the bandwidth is, the higher the range resolution is, which we get. And we can, for example, the basis of any 4G or 5G communication system is the so-called OFDM technology, orthogonal frequency division multiplexing. Here you have a resource grid in time and frequency, which is depicted by those boxes. And these so-called resource elements we can reuse both for communications and sensing, or we can insert new dedicated resource elements for sensing. Even, for example, each cell can insert specific sensing symbols in order, for example, to avoid interference between different cells.
Once we have embedded these sensing capabilities in cellular communication systems, we can support really a rich variety of different use cases. Think of the indoor factory scenario. Here we can better support the cooperation and coexistence of humans and robots. So in factory environments, sensing can help to detect AGVs, pedestrians, for safety purposes and also for asset tracking in the factory. Any objects not requiring a particular modem as an equipment can be detected by the sensing system. Then when you look at the outdoor use cases, there is a variety of possibilities to support smart city systems for monitoring the traffic in streets, for tracking pedestrians, and thus enhance the safety of vulnerable road users. So at street crossings, intersections, we can prevent that accidents to some degree happen. Furthermore, for drones, you want to be, for example, be able to support intrusion detection or geofencing use cases to monitor the lower airspace for drones, and thus also to enhance safety in society.
Network as a sensor will offer us a rich set of new use cases, new features which can be integrated into cellular communication systems. This can be detection of drones in the lower airspace. It can be detection of pedestrians or robots in the factory. It can be monitoring of traffic for smart cities or for parking lots. And in order to make all of those use cases useful and make them happen, of course, there is still some research required. And this research stretches across different technology building blocks. So for example, we need to be able to model the channel, so the propagation channel. In conventional cellular communication systems, there are channel models, statistical channel models from transmitter to receiver, which help to simulate the performance of communication systems. Simulation is very important because before you build a system in a large scale, thousands of base stations, you're not able to assess its performance because for prototyping you have only a few of them. So you need to be able to simulate systems. And for joint communication and sensing, of course, there are challenges which need to be solved before we can simulate it, because what is new in these joint communication sensing systems is that we need some deterministic description of the propagation channel. Statistical description alone will not help, because there are certain geometrical properties of objects which have to be inherently there in the simulation. This is one problem we have to solve. And then the other problem is also that we have not only a transmitter and a receiver, but we have a transmitter, a reflection, then we have certain reflection properties, and then the channel back to the receiver again. This is one part of research challenges which we have to solve. The next part is that typically we use higher carrier frequencies for sensing. The higher the carrier frequencies, the higher is the bandwidth. The higher we have the bandwidth, the better is the range resolution, so we can more accurately localize, for example, objects. But if we go to higher carrier frequencies, usually with wider bandwidths, we have more power consumptions in the analog to digital converters. This means we want to have not so many digital chains, and therefore in those systems typically hybrid beamforming is used. So a combination of analog beamforming plus a few digital processing chains. But this means that the beam can only look into one direction at one time. And so we need proper beamforming technologies. How do we scan properly the environment over time in order to perfectly reconstruct the information from the environment? The next challenge we have to solve is the duplexing challenge. So if we have what the radar world is causing a monostatic setup, meaning the transmitter and receiver are nearby, we have a self-interference problem. So we have not only the reflection coming back from an object, but we have also a spillover of signals from the transmitter to the receiver. And this self-interference problem has to be handled. Ideally, we would have a full duplex system, but this is not necessary. We can make sure by proper smart separation of transmitter and receiver, smart digital interference cancellation, plus the appropriate beamforming strategies that we can deal with self-interference also without full duplex. And then, of course, we need to have the proper quality of service established. Quality of service is well defined for communication systems, but we need new definitions for sensing systems. And we need to take into account the existence of quality of service both in the communication side as well as the sensing side. And then there's not only the base station and the antenna array, but there's also other network elements. In localization for 5G, we have the so-called LMF, the localization management function. This now should be expanded. So this aggregates signals from multiple base stations in order to collect the information about, for example, the location of an object. Now we would need this to be expanded towards the functionality of sensing, and we will need the proper protocols to connect all those entities in an interoperable manner. And then I mentioned already that we of course also have challenges to solve in the way how we, for example, train AI/ML systems. Nobody wants to hand label radar images and train based on this. So we need also new clever ways of using our artificial intelligence properly. Let me give you an example of technological solutions which come from Nokia Bell Labs in order to address the challenges I mentioned previously for sensing. So regarding the hybrid beamforming challenge, we have come up with a solution which we call SARA, Sampling and Reconstruction of Angular Domain. The conventional codebook of beamforming is typically based on a uniform angular design. We have come up with a new normalized angular frequency domain design combined with a specific interpolation, and this design is very, very efficient. So we can scan the environment and depicted by the blue dots, and then reconstruct the green response of an object perfectly, even if we have just discretized and sampled the space in a certain manner. And this reduces the beam overhead compared to conventional uniform angular design by more than 30%, and is also very efficient in terms of computational complexity and can also achieve a very good resolution of objects. A second technology example I like to deliver is about the way how we sense and then train artificial intelligence systems. So, for example, neural networks without the need of labeling each radar reflection. So on the left side, you see, for example, the image of a street crossing where there is a car, and then leftmost, there is the radar parallelogram, so the radar image of this. So it looks, for a human observer, it looks confusing, and it's not easy to label where really the car is. And so our technology is now using camera information in order to localize the object of interest, and then based on this localization, find the bounding box in the radar image, and then use the cross information to train the neural network. So this is a self-labeling technology, which is referenced in the reference on the left side. Let me conclude. So we can really say that network as a sensor becomes an enabler for the vision of connected world. And it can already be realized in 5G Advanced partly, but we recommend to have a design which is integrated natively into the air interface of a 6G system. And thus we think that sensing will unleash its full potential in 6G. And you have seen that we have really good progress in key network as a sensor technologies. I've given you specific examples in areas like, for example, AI, ML, and beamforming. Thank you very much.